So back when we integrated, let me do something easy. The integral up to x dx, that's simply x squared plus some constant of integration. And that's just a number. And that's because if we take the derivative of this, the derivative of x squared is 2x, and the derivative of a constant is just 0, which is simply 2x. And that's going to take us back to the integrand that we had at the beginning. Now, when we integrate functions with more than one variable, well, that constant of integration is not just going to be a number. It could be just a number. However, that constant is a function of, in terms of the variable for which we are not integrating with respect to. So, for example, okay, let me give you the idea. So for example, if we integrate some partial derivative with respect to x, well, we're going to get the original function f of xy plus c. But in this case, since we integrate it with respect to x, that constant of integration will be a function of the other variable, of the other dummy variable, which in this case is y. If we integrate with respect to y, that constant of integration will be a function of the other variable that wasn't involved in the integration. So let me give you a couple of examples to show you how we go about the partial integration. So, and just like in regular integrals, so a very common practice was to take out the constant and then just worry about the remaining part of the integrand. We're going to do something like that for partial integration. Since we are integrating with respect to x, I'm going to take everything else outside, everything that is constant outside of the integral. So I'm just going to take the y because this 2x is useful for finding the integral, which is x squared, all right? So in this case, the integral of 2x is x squared times the constant y plus c, but in this case it's not just a plus c, it's a c, a function that depends on the other variable that we didn't integrate with respect to, in this case, y. And in the same way, if we partial integrate to xy, but this time with respect to y, the integral of x, or rather to y, dy, take out the constant x, and well, that's y squared times x plus c. In this case, it's a function of x because we integrated with respect to y. So what's the thing here? If you take the partial derivative, with respect to x, so this is 2x y plus, since we are differentiating with respect to x, what's the derivative of something that depends on y?
0.
It's 0, all right? Because it's constant, right? And the same with respect to x, all right? Now, what if we had 3 variables in this case? Well, it's still the same thing. Well, number one, let me do the integral. Let me do something on the side. The integral of e to the 5x. That's itself e to the 5x, but in this case times 1/5. Times 1 over the constant. In this case, we are integrating with respect to z. Everything else, in this case x and y, will be constants. That means that's equals to e to the x y z times, instead of 1 over 5 like in the previous example, or the side example rather, 1 over x y. But in this case, the constant of integration will include all the variables that we do not include in the integration. So in this case, since we integrated with respect to z, this c will be a function of x and y. All right. So that's how partial integration goes. It's the exact same rules of integration. I mean, like general power rule, possibly even a use of by parts, partial fractions, whatever method you can think of. Just keep in mind that we're integrating with respect to one variable for now. All right. And well, so when it comes to definite integrals, because these were indefinite integrals, how do we deal with definite integrals, which is in this case applying the fundamental theorem of calculus? For example, the integral from 0 to 1 up to x, that's x squared evaluated from 0 to 1. And in this case, we plug in 1 wherever we see the letter x. That's 1 squared minus over 2 minus 0 squared over 2. And which is in this case a 1/2. All right. How do we apply this to functions of multiple variables? Well, in this case, keep in mind that we are integrating with respect x. So the integral of 3x squared, this will be 3x cubed over 3 plus the derivative, the integral of y with respect x is just a constant times x, which is xy, and that gets evaluated from 0 to 2y. Now be careful, because we see too many variables here and we have limits of integration. Where do we apply those limits of integration? Only we plug this only on the variable that we integrated with respect to. In this case, since we integrated with respect x, we will evaluate this to y and 1 wherever we see the letter x only, leaving y as a constant. Okay, so let's go ahead and do that. All right, number 1, let's simplify 3 over 3. That's x cubed plus xy from 1 to 2y, and that's 2y cubed plus 2y times y, and in this case 2 cubed, which is 8, y cubed, and plus, actually I forgot, minus 1 cubed plus 1 times y. All right, notice I'm only plugging in that 1 for the variable x. And well, so that's 2y squared, and this is going to be 1 plus y, that's minus 1 and minus y. And well, there's really nothing to simplify any further here, no like terms, so that's our final answer. So in the end, again, check how the integral, a definite integral in Calc 1 or in Calc 2 gave us a constant, a numerical value, which is just a number. So it's a number. In this case, we're also getting a constant, if you will, but this constant is with respect the variables that we are not integrating with respect to. In this case, there was only one additional variable besides x, it was a y. So let's look at letter B. The same integral, but this time with respect to y. And we're going to integrate it with respect from 1 to x. Well, so what's the integral of 3x squared with respect to y this time? 3x squared y, because 3x squared is constant with respect to y. So 3x squared y plus the integral of y with respect to y. Well, in this case, we use the general power rule and integrate between 1 and x. So this will be, and careful again, because these limits of integration are not just going to go anywhere. They're just going to go, since we are integrating with respect to y, we will plug them in only where we see the letter y. So let's plug in upper minus lower limit. That is 3x squared y, which is x, plus x squared over 2 minus 3x squared times 1 minus 1 squared over 2. And in this case, well, so that's 3x cubed plus x squared over 2 minus 3x squared minus minus, it's plus 1/2. And in this case, we can combine like terms, not like the previous example. We can combine the square terms, the quadratic terms. So in this case, 1/2 minus 3, that should give us negative 5/2. And that's our final answer. So that's how we treat partial integration, well, without limits and then with limits. All right. Okay, so let's have a look at the next page. What do we have on the next page? Another definite integral. In this case, we are going to integrate. It's a simple integral, but in this case, we have multiple variables. And in this case, we are integrating with respect to x. So just so we don't get too confused, how about we take out all of the constants? In this case, cosine y is constant with respect to x. That's because we're integrating with respect to x. So cosine y, integral from y to pi over 2, that's sine squared x dx. So now we can focus on the integral that only depends on x. Alright, so now here is where we will need our calculus 2 technique. So let's see, let's integrate sine squared. Would a u substitution work here? Definitely not, because the derivative of sine is cosine, and we don't have a factor of cosine multiplying with the dx. So I think we will have to use our power reduction formula. So we will have to use sine squared theta equals 1/2 1 minus cosine 2 theta. So that's the one for sine squared. The one for cosine squared, it's exactly the same, but instead of a minus, it includes a plus this time. Alright, so let's apply the formula. Let's use the trig identity. So that's cosine of y, integral from y to pi over 2, and that's 1/2 1 minus cosine to, oh, and it's not to theta, it's to x. Well, so how about we take the 1/2 outside and distribute this into two integrals. So I'm going to take this 1/2 cosine y, integral from y to pi over 2. And at the same time, I'm going to distribute this into two integrals. That's the integral of the x, and minus 1/2 cosine y, integral from y to pi over 2. And that's cosine of 2x. And while these two integrals are pretty straightforward, we can integrate dx, which is just going to be x. So I'm going to leave a space for something here. So that's an x minus 1/2 times 1/2 the integral of cosine 2x, which is sine 2x, and evaluate it from y to pi over 2. And outside I'm going to have this common factor of 1/2 cosine y. But again, be careful here, because one thing to keep in mind is that we are integrating with respect to x. So we're not going to plug in these limits of integration to every single term factor in our antiderivative here. These ones are going to be evaluated only whenever we see the letter x, because we integrated with respect to x. So let's go ahead and do that. So that's 1/2 cosine y, and that's pi over 2 minus 1/2 sine of 2 pi over 2, which is evaluating this. And then so that's minus y minus 1/2 sine of 2y. Alright, so let's simplify these trigonometric expressions. Well, sine of 2 pi over 2, well, it's the same as saying sine of pi. And what's sine of pi? 0. And well, that's going to leave us only with the following. So the 1/2 cosine y times pi over 2 minus y, because we're essentially distributing the negative sign here, negative y, and minus minus, that becomes a positive 1/2 sine 2y. Alright, no plus c in this case, even though it's all variables, mostly variables, but again, we already did some fundamental theorem of calculus, so technically this is all y's, which is constant with respect to x. Right? Let's see what's next. All right. So the next topic, we call it iterated integral. So that's another way to say multiple integrals. And we're going to do double and triple integrals. Double and triple integrals. In some cases, the problem, we won't be able to solve up a problem using x and y's. We will have to convert the problem into the polar system. Remember polar coordinates from calculus 2? So that's coming back. It's the last handout I gave you. And later, when we do triple integrals, that's going to be its own section. We'll move on to another section in which we will introduce 2 new coordinate systems besides the polar, which is the cylindrical coordinates, which is basically the 3D version of the polar system. It's a circular base and well, a height of z, that becomes a cylinder, and we're going to use also the spherical coordinates. Alright, so in the meantime, let's see how these iterated integrals work. So we're going to have a double integral, so from 1 to 4 and from 0 to x for the function 4xy minus y plus x, first with respect y and then with respect x. So notice in this case how we mentioned that we work from the inside out. In other words, we have to do this integral, do this number 1, whatever we get, do a second integration, well in this case with numbers. Alright, so let's have a look at this one. So number 1. Okay, so let's integrate 4xy with respect to y. So in other words, we're going to have we're going to integrate y squared. Everything else will be constant, so that's going to be held constant. So that's the integral from 1 to 4 times, well, whatever we get from the integration. So that's going to be 2xy squared. And then the integral of y with respect to y, that's a minus y squared over 2 plus the integral of x with respect to y, but the x in this case it's constant, so we're multiplying, so we're just getting x times the integral of the y, which is going to be xy. These will be evaluated from 0 to x, and don't forget this dy. So we're going to apply the fundamental theorem of calculus for this function, but again, recall that we integrated with respect to y first. This x and this 0 should be substituted only wherever you see the letter y, because that was the variable. Yes?
Shouldn't it be dx at the end?
Which one?
Yeah.
Yes, yes, that's an x. Thank you. Yeah. And so let's do this. So that's the integral from 1 to 4. So that's a 2x. Okay. Whoops. Yeah. So that's going to be 2x times x squared minus x squared over 2 plus x times x. Now, The good news, this lower limit is 0. Do we agree that if we plug in 0 here, 0 there, and 0 on the last term, everything is going to get zeroed out? Okay, so it's valid to just say minus big 0. It's all right on the exam or anything. This move is valid. And well, that's going to leave us with the integral from 1 to 4 of 2x cubed minus x squared over 2 plus x squared with respect to x. But of course, it looks like we have like terms. So negative 1/2 x squared plus 1 x squared, that's going to reduce to, so that's 2x cubed plus 1/2 x squared. All right. And well, the problem is now reduced to a regular single integral. All right. One single variable, all x's, and with respect to x, so we would expect to get in this case a single number as a final answer. All right, so let's go ahead and simplify this. Integrate this. So that's 2x to the 4th over 4 plus 1/2 x cubed over 3, evaluated from 1 to 4. So 2 over 4 reduces to 1/2, and 1/2 times basically 1/3 reduces to, so that's 1. Let me do x to the 4th over 2 plus x cubed over 6 from 1 to 4. And from here, let's apply fundamental theorem of calculus. So that's 4 to the 4th power over 2 plus 4 to the 3rd power over 6, that's the upper limit, minus 4 cubed over 6 minus 1 cubed, and then over 6 is over 2 and over 6. And after simplifying all this madness using a calculator, our final answer has to be, which one?
Second part, you before the third.
Oh yeah, this one should be 1, right? Thank you. 138. All right, so let's see. Let's do another one. Describe the graphs. Well, actually, there's a little typo here. Okay, look about this. All right, so let's evaluate the integral from negative 4 to 4 and 0 to x squared of the quantity 6 square root of 64 minus x cubed with respect to y and then with respect to x. All right, so lucky for us, the order of the integration first goes about with respect to y and then with respect to x, because otherwise, if it were dx dy, well, if we try a u substitution, the derivative, which is going to be negative 3x squared, we don't have a factor of x squared outside of the integral, so we can use the u sub. So in this case, well, all we're doing is integrating the innermost. We're doing the innermost integral, which is, well, that radical is just constant with respect to y. It's like integrating 5 dy. See what I'm saying? In the integral of 5 dy, it's going to be just 5y. Well, it's not 5, it's this crazy looking radical. So negative 4 to 4. So that's square root of 64 minus x cubed times y. And in this case, we go from 0 to x squared, and then don't forget the dx. But again, notice in this case that we're integrating with respect to y. That means these limits of integration are just going to go here with the y, leaving the x alone. All right, so this means the integral from negative 4 to 4, that's the square root of 64 minus x cubed, and then upper limit, which is x squared, minus lower limit, which is 0, and then with respect x. And of course, x squared minus 0, it's just x squared. So the integral from -4 to 4, that's a square root of 64 minus x cubed times x squared dx. And now we may be able to compute this integral, because if we look at the quantity multiplying the dx, which is x squared, it's 1 degree less than what we have inside of the radical. So the du setup is going to work just great. All right. So let's go ahead and do u equals to 64 minus x cubed, and du equals negative 3x squared dx, where x squared dx equals negative 1/3 du. And well, so if you don't want to back substitute for this binomial 64 minus x squared and having on top of this radicals, how about we also change the limits of integration? Even though technically this is the correct way to go about and integrate a definite integral, would be use a u substitution, because if we're changing the integral to the world of u to solve the problem in an easier way, then we also have to change the numbers to the world of u as well. All right, so let's see. So u of -4 equals 64 minus -4 quantity cubed. But well, -4 cubed is negative 64 times the negative outside is positive 64. So 64 plus 64 is 128. And u of 4, that's 64 minus 4 cubed, which in this case it's going to be 0. All right, let's integrate. Let's write down the integral, not from -4 to 4, so this time from 128 to 0 of the quantity square root of u du, and actually this needs the correction factor -1/3, which I'm going to write it outside. And well, so many students freak out when changing the limits of integration to the world of u, because check this integral, how the lower limit is a larger number than the upper limit. So when students see this way, they're like, wait, hold on, that looks weird, maybe I did something wrong. No, that's fine. That's very common when doing a u substitution with limits. However, if you don't feel comfortable with this order of the limits, you can use a property of a property of integrals, the one that says that when you have the integral of f of x from a to b, you can reverse the limits of integration from b to a, provided just change the sign of the integral. All right, that's one of the properties for the geometric properties, because it's like finding the negative in area, so all we do is reverse the limits. And in this case, well, we can actually use the sign right here, right? The negative sign, get rid of that negative sign, make it a positive, and change the limits. So actually I'm going to do u to the 1/2 and du. And this one can be integrated just using the general power rule, and that's 1/3 u to the 3/2 over 2 from 0 to 128. Okay, so let me continue over here. I'm going to erase this one so I can have enough space. This was just a remainder of what it is. And so that's 1/6, and that's going to be 128 to the 3/2 minus 0 to the 3/2. Well, 0 to the 3/2 is just 0, but 128 to the 3/2, well, recall that we can go about radicals in this case. Whenever we have a to the m over n, when we have rational exponents, in this case we can write this using radicals. And one thing to recall is that the denominator of a rational exponent is the same as the index of the radical. However, there's a couple of versions of this property. This is one, and the other one has the m power outside of the radical. And in this case, in some cases, it's more convenient to use one or the other. So for example, it's good to use the last version, the second version, whenever you know that that number is a perfect square or a perfect or whatever root. Because in this case, if you want to evaluate, for example, 64 to the 7 halves, all right? One way would be 64, the square root of 64 to the 7, but you don't want to do 64 to the 7 because it's such a big number, isn't it? Instead, do 64, the square root of 64, which is 8. That's a relatively smaller number, and then just raise it to the 7th power. I mean, it's still going to be a big number. But in this case, since the number 128 is not a perfect square, we're going to use the the first version. So that's a 1 over 6.
Because there shouldn't be 2 9s.
2 9s? Yes, I don't know where I messed it up. Yes. Over 3 over 2, right? Yes. Thank you. I thought it was like integrating just u, right? 2 over 9, and I just divided by 2. Thank you. So 2 over 9. And well, that's going to be 128 square root 128 cubed, which is 2 over 9 root of 128 squared times 128. And in this case, we may just go about factoring out the perfect square, which is 2 9s, 128 root of 128, which is in this case 256 over 9, 128, root of 128. But I think we can further simplify the square root of 128, because that's 64 times 2, right? So 64 times 2, and that's 8, so 256 times 8. Oh, that's going to be a big number. I didn't have this number, so that's why I'm going to do it by hand. Or can anyone help me with the square root of 8 times 256? 2048. 2048 over 9, or root of 2 over 9. All right. So that's final answer. And let's see.